to you so that you can go ahead with the presentation. Please feel free to share your screen.
Okay, thank you very much, Jude. Hello to everyone. Good afternoon, good morning, good evening from wherever you're joining us. Can everyone hear me clearly?
Yes, we can hear you.
All right, great. So I'll just quickly share my screen so that we have some few slides before we get into the real deal.
Yeah, so while Mr. Desmond is sharing his screen, since this is an interactive session and it's a hands-on session, please, you can, if you have questions, just keep them for the end or you write them in the chat, and then we will take care of the questions at the end of the session. Also, this session, we will provide e-certificates to those of you who are interested. So if you don't, you can provide us with your name, your full name, how you want it to be on the certificate, as well as your email address. Please provide that to us in the chat, or afterwards you can send us an email with this. Then we'll prepare the certificates in the weeks ahead and send to you. So go ahead, Mr. Desmond. Thank you.
Okay. So I just shared my screen. I'm sure you can see my slides, right?
Yeah.
Okay, so thank you very much once more, Jude, for this opportunity. So in the next 1.5 hours, we'll be talking on R, basically. Jude has introduced everything, so we'll just dive straight to introduce what this software is all about. I'm sure there are people here who've heard of the software. Some people have used it. Some people are already in the field. Some people are just here to maybe get some extra knowledge. Some are newbies in the whole thing. So we'll try to keep it as simple as possible. So we'll have just some few slides on introducing what the software is all about. And then for over an hour, we'll have hands-on exercises. I already have some scripts that I've arranged, which I'll run them and explain what those scripts are all about. I try to make them as basic as possible because R can be very, very complex at some point. So, but we try to make the codes as simple as possible such that anyone who is just a starter into the software can be able to understand from there. So we'll try to keep them as easy as possible. And again, like Jude earlier mentioned, you can keep your questions. At the end of the session, you ask your question, and if there's something that you didn't understand, we can always go back and I explain again. But one thing I want to advise is when it comes to statistical analysis or data analysis using any software, be it from Excel, SPSS, R, SAS, Python, whatever software, it's all about practice. It's hands-on. It's not about slides. It's not about providing you PowerPoints or handouts and so on. If you really want to be proficient, or if you really want to be enthusiastic and really develop so much interest when it comes to statistical analysis or data analysis in general, you have to practice. So the slides as well as the codes we'll be sharing with you are some of the codes of data sets that we'll be using to teach students, and some of them are data sets that we've analyzed over the past years. We've just put them together to see how we can introduce some of these concepts. There is so much that we will not touch because of time, but we'll try as much as possible to introduce the very basics, so you can actually have an overview and appraisal of how this software can be used to analyze data. So again, we will talk about R. This is a famous logo that you tend to see. And I show this logo so that if you maybe want to go online to download this software, you might be wondering, okay, what am I going to download? Am I going to download the base R or the R RStudio and so on? So this is the logo for R RStudio. But there is also base R, which you can find on my screen. The one with just the R without the blue circle. So this is the base R, and then we have the R RStudio, which is the blue circle with the white R in the middle. So these two softwares are basically the same thing. The same thing as in they were developed for the same purpose. The difference is that the base R was developed first, and then after some years, they now decided to come up with a more user-friendly version. But again, you cannot use the user-friendly version without the original background software. So the base R, the one up, is just like the engine of the whole thing, and then the R RStudio is like a vehicle. You have the engine and then the cabin of the car. So R RStudio is a more user-friendly version. So when you go on RStudio.com, for example, to install this software, you need to install both of them. You install the base R, and then you install RStudio, because RStudio works on the algorithm of base R. Because if you install just RStudio on your computer, you will not be able to use it, because RStudio is just a friendly interface, a more flexible and more interactive friendly interface. But the computer algorithms actually are being run on the base R itself. So it's always important to install both of them. We want to install. I'll show you how to install them, and the links is very easy. This software is free and it's open source, right? So you don't need to pay for it. There are versions that you might want to pay, but this is for really, really advanced users, people who want to develop packages and stuff. But for every other user, for your analysis, for your research projects, for your freelancing and so on, it's okay to use the free software. So you don't need to be scared to download. No one should tell you they have the software for sale and so on. So you can always go to rstudio.com and you download the setup and you install it into your computer. As well as the RStudio, which is a more user-friendly version, you can also install, and you don't necessarily need a good internet to be able to use this software. Yeah, you need internet at times, maybe you want to install a package or so, but for the software to actually run, you don't need to be connected to the internet. It means that you can effectively analyze data, even if you're found in a very, very remote area. You can be able to analyze data, but there are some other things that you might not be able to do, maybe installing packages. But if maybe you're going for a field work, for example, where there's no internet, like you're an epidemiology, you're a public health expert, you might decide to say, okay, maybe I install all the packages that I need to use before going to the field. When you're in the field, you can effectively analyze your data and do everything you want to do. But again, we're in the 21st century, and we cannot really overemphasize on how important the internet is, especially when you want to get into the field of statistical or data analysis, because you need to always search some certain things online, etc., etc. But again, the internet is, is not a prerequisite, but again, it's very important. So like I earlier mentioned, this software is free. You can always visit the CRAN. The CRAN is a comprehensive R archive network. So what does this mean? This is like a project that has been developed online where everything concerning R has been stored. So if you visit this website, the cran.rproject.org, you can find the software, the software package. You can find videos, you can find tutorials, you can find even different packages and so on. So the CRAN is just like an archive of network where different things related to R you can be able to use. So if you need a particular package means, you can go to our archive network. If you are looking for maybe links that can help you to understand, or tutorials or videos and so on, you can be able to go to CRAN. So most of these things, all of these things literally are free. So it makes it very easy for you to study R. Easy in the sense that you don't really need to buy a lot of materials. Most, or even everything when it concerns R is free online, is really available. You just need to know where to source whatever thing you want to source. And again, this software is open source. Open source means that anybody can add whatever they want to add, but you should be adding something that makes sense. So there are actually functionalities that are being added into this software every day. That is why if someone tells you that they want to teach you everything about R, then it's practically not possible. Because how can you teach someone everything about a software that is open source, a software that by the end of tomorrow will have 50 new packages that have been added? So there are statistical programmers who keep discovering new packages for doing different things, for plotting different kinds of complex graphs, for doing different kind of genome analysis, that they now keep adding these different packages into the software to make it very easy. So they try to make the software as flexible as possible, in such a way that the software should be able to replace other software like SAS, like Stata, like even the GIS for those who are doing geographical information system, who draw maps and so on, people who are into genetics and genomic analysis, people who are into bioinformatics and so on. You can be able to use R. Why can you be able to use R to do all of these different diverse analysis? Is because we have different packages. And these packages are simply folders or simply programs that have been stored into this software, which you can just download from online. For example, if I want to plot a graph, I know that, okay, maybe I want a very complex 3-dimensional graph. I don't just open my R RStudio and I start plotting a graph. No, there is a package where the functions that we need to plot a graph have been installed in that package. So I need to go online, I download that package from the internet, and I can be able to use the functions there to instruct R to plot in a certain type of. So throughout the session, you keep hearing, I'll show you how we install a particular package. There are different packages that you use to do different analysis and so on. So there are so many, there are hundreds and even thousands of different packages, which people keep adding every day in order to ease the usage of this software. And we also have some free tutorials and some instructions online that you can always check. There are free books that you can always read if you really want to get into the details of these things. R also is capable of producing automatable research. So if I do something in R, I should be able to send you my script and you reproduce the same thing. I don't need to even send you the results. If you can be able to use the software, I just need to send you the codes that I used, and you open those codes on your R Studio, you run them, and you should be able to get the results. So it's automatable because you're not manually doing these things. You just need to write the code and the software automatically generates the output for you. That is what programming is all about. SAS, Python, all the softwares, that is what they do. So what we'll be doing here is showing you how to write some of these basic codes. From the beginning, it might be very challenging because it's like learning a completely new language. But again, take for example, you get a scholarship to study in China. If you want to be able to write an essay in Chinese language, for example, you don't just start writing an essay. You start by first of all learning the letters of the alphabet. From there, you can be able to construct words. From words, you can now be able to construct maybe sentences and phrases, and then a paragraph. From a paragraph, you can now come up with maybe an essay. It's the same thing with programming. Programming, you cannot start analyzing data in programming without learning the very basic syntax, the very basic things that you need to put together in order to develop a long list of codes, which you can now be able to use to maybe plot a graph, or maybe to do a regression model, or to do a t-test, or to do a chi-square test, etc., etc. So we'll see some of those things. And it also has a fine control of graphics. You can plot different graphs in R, three-dimensional graphs, and so on and so forth. There are so many different graphs you can plot in R. Of course, you can conduct statistical analysis, like what we'll see. We'll do some statistical analysis, like regressions, like the chi-square, t-test, the basic ones. You can do advanced multivariate analysis. You can do genome analysis. You can do bioinformatic analysis, and so on. You can display your results graphically. You can also manipulate your data. Maybe you're working in a project, or maybe in a research organization where your role is just to clean data. They collect data from the field and give you, and your role is just to clean the data and get it ready for someone to analyze. So what you'll be doing is now you mostly be studying packages that are used to clean data, like the tidyverse packages, like the zpair packages. We'll see a couple of them. You see how you can merge data sets together, you can subset, you can cut, you can rename, you can look for missing values, etc., etc. You can do all those things with R. So the usage of this software is so diverse. There are a lot of things you can do. You just need to be able to understand how and when do you need this software. What are you really interested in? Then from there, you can now really start sourcing what are the packages that you can use in order to be able to effectively analyze what you really want to analyze. So on this graph, it shows us the rising use of this software from 2000 when this software was discovered. So it's just 25 years old. And you can see that fields like mathematics, neuroscience, and so on, agriculture and biological science are increasingly using this software. So this data is up to 2015. So you can imagine 10 years to now, the amount of fields that are using this data. People now into business now are widely using this data, econometric analysis, people into management, into social sciences, and so on. So you can see this is a software that is being used by different people, earth and planetary science, environmental science. So you just need to know what you want. By the end of the day, the syntax is the same. The code that you use, the way you type your code in someone, if you want to do an environmental science analysis, is not different from someone doing a neuroscience analysis. A full stop, a bracket is the same. The difference now is what type of analysis do you want to do? You need to understand how your data is and whatever, but the syntax, the programming language is the same. The difference now is the statistical analysis that you want to do. It might vary based on your field of study and so on and so forth. And like I earlier mentioned, you know, R has a very, very fine control of graphics. But again, there are other softwares that are being used to plot graphs like Plot. like Power BI, which have been used to present data, but R also has a fine controller of graphics. At times you study, or maybe you look at journals and you see beautiful three-dimensional graphs, heat maps, and so on, distribution maybe of disease prevalence, of disease incidence, and so on. You see how it's been distributed all over the world, and they show you three-dimensional graphs and so on. Most of those things are being drawn using programming languages, because with programming language, you can instruct the software to do whatever you want it to do. Not like whatever, but to do as much as you want it to do. You can really instruct it very well and say, plot this thing over and over, repeat this over and over, repeat this particular analysis over, plot this line 2 times, plot this one vertically while you can plot this other one horizontally. You can give it several instructions at the same time using one line of code. That is very important. So you can see a single graph being plotted on maybe 15, 10, 5, or even 20 lines of code, because it's giving different instructions and different syntax are involved for it to do different things on the same plane of the graph. So we'll see how to plot some of these basic plots, like the common bar charts that we see every day, the scatter plots, and so on. And I'll show you how you can plot that. From there, you can now be able to expand and expand and expand to whatever level you want to. Now, enough of all the talking. Let's get to the real deal. Let's see what this software is all about. For those of you who have the software, of course, you might be used to the interface, but I'll just show you the interface, how it works, and then we import some data sets and we do some hands-on exercise. Like I said, if you want to install the software, you can just go to RStudio.com, and you get the setup for both the R and RStudio. And again, you need to have a 64-bit laptop. It's advisable to have a 64-bit laptop so that you can install the 64-bit setup and you can be able to use for analysis. So I'll just quickly switch to my RStudio interface. So let me just put it by default the way it's supposed to be. Let me. Okay. I'm sure you can see. Let me try to make my screen a bit bigger. Let me zoom out. Okay, so you can see my RStudio, right?
Yeah.
Okay, so when you open your RStudio, this is what you see from the beginning. It has 4 different windows. From the first start, it looks very complex because you see a lot of functionalities, a lot of options there to do so many things. But again, it doesn't need to scare you. For you to analyze a data, you don't need to make use of all these functionalities at the same time. No. There are some functionalities here that you might never use because it's not necessary for your analysis at that particular point in time. So it has this software actually has 4 different windows. If you see this, we have the top left, the top right, the bottom left, and the bottom right window. And these 4 different windows have different functions, and you can actually separate these windows. For example, to the left, you can actually minimize this one. Maybe I really want to make use of the top left window more. I can minimize the bottom one, as well as I can pull it all back. And then we can also minimize the right window and so on. So based on the window you really want to use, you can minimize the other one so that you have more space on your computer to work, because you don't necessarily need to make use of all the 4 windows at the same time. And among these 4 windows, the top left window is what we call the source. You can see we have the source here, and this is where you type your codes. If you can see here, I have a whole lot of scripts that I've written, which we use over 100 of them. So this is where you type your code. So it's like your notebook, because you can actually type the code here and erase it and edit it, copy and paste. So this is where you type your code. So if I send you a script of codes that I've analyzed and you open on RStudio, this is where the codes open. And then we have the bottom left. Below that window, we have the console. So this console, this is where we run a code here, the results appear on this console window. So if you write maybe 1 + 1, for example, say if I type 1 + 1 and I run, you see it gives me 1 + 1 and it gives me the results 2. So this is where the results appear, and you can always clean it out You see on the top right of this console, you see there's an icon there that looks like a broom. You can always, maybe you've made a mistake and you just want to wipe everything, you can always wipe it out and so on. And then on the top right, we have some other windows which are more of, they just save some information like the environment, for example. The environment just saves a history of object names and data sets that you use. So here you see a lot of things, a lot of names that are not in yours, because I've been using my R RStudio for a while. So you see a lot of different things in my environment. The history also keeps a history of codes that you've typed and so on. Here you can always erase them. This is just a history, right? So you can always, maybe you forgot something you did the day before, you forgot to save it, for example. You can go to the history and maybe trace that code, which was very important for you, and you reproduce the code to do something else and so on. And on the bottom right, we have a very important window, which is the plots. So if you plot a graph, if I type a code to plot a graph on the source and I run it, if the code is well written, no errors, then the graph will display on this bottom right window. We'll see an example when we plot a graph. Beside the code plots, we have another window called packages. These packages here, it has different packages, which I'll explain to you what the package is when we're installing one of them. There are different packages that are being used to do different analysis, which we'll see later. And what I usually do is I always like to, so you can always interchange these windows, right? You can decide to take this one to the right. Like, for example, what I usually do is I switch my console to the right. So if I want to switch my console to the right, I can just go to View, and I go to Panes, and I switch my console to the right. I always prefer to switch my console to the right because this environment window, I hardly use it. So I just minimize it. And so that if I type my code on the left, I can see my results on the right. So the two windows, the most used windows, are adjacent to each other, so that I can type a code and I see the results on the right, and it's very easy. It's just more user-friendly. That's the reason. It's not like you must do it that way. And then on this source window, if you go top, you see some icons, file, edit, code, and so on. File is just like the file we have in our Microsoft Word. If you click on it, you see you can save. Maybe you type some scripts for an analysis. You might want to save it. You might want to open a new file. You might want to close it. If you want to open a new file, for example, if you click on new file, it takes you RScript. If you click on RScript, you see it opens a new page. So this is the page adjacent that I was working on, and I've opened a new page, which is a blank page, which I can start typing my codes and save it at the end of the day and so on. You can also edit, undo, redo, cut, copy, paste, select, all those basic things that we all know. View, you can zoom in, you can zoom out, maybe you want it bigger, you can go to the next tab and so on and so forth. Plots, these plots here, maybe you've plot 5 different graphs, you can go to the next plot, previous plot, you can zoom your plot, you can save it as an image, as a PDF, you can copy the plot and paste maybe on your document and so on and so forth. Session, this is a very important tab that we use. If you want to set your working directory, I'll show you what setting a working directory is in a couple of minutes, and so on and so forth. There are so many other functionalities here that you don't use on a regular basis. The help page is also very important. So there's a help page in R that you might want to, maybe you're doing an analysis and there's something you really don't understand. So R has some kind of like an inbuilt dictionary. But the dictionary is not an English dictionary per se. It's not a dictionary where if you type what is computer, R gives you the definition of computer. No, it's a dictionary of functionalities in the software. For example, what is mean? What is median? What is mode? Or what is the function to do this? You know, if you're using a particular function, I don't really understand what the meaning of the function is, you can do a help page in R. For example, let me show you an example. I might ask R, what is mean? So for you to know what mean is, you just type question mark and the name of the word. Mean, because Aru knows the word mean. If I ask Aru what is house, Aru doesn't know what house is, because house is not a function that has been inbuilt in a system. So it tells you that there is no documentation for house. But if I ask Aru what is mean, you see, Aru gives me a help page down here. It tells me arithmetic mean. It says it's a generic function for arithmetic mean, and then it gives me how you can be able to compute a mean in a data set, and gives me so much, and even references and some other things that you can be able to use to understand what mean is. So again, you can be able to use R as a dictionary. But for you to really be able to do this, you must know what you're looking for, maybe the name of the function, and so on and so forth. Again, we'll use some of these things as we go through the tutorials in a couple of minutes. Now, if you have a code, for example, let me type maybe 1 plus 3. How do you get the results of 1 plus 3? If you see here, there's a blue arrow pointing to the right, which shows run. So if I want to get, if you type 1 plus 3 on the source, if you want to get the result, you just click on run. You see the results appear here 4, or you can use the shortcut, which is Control Enter. So, you know, because at times it's very boring to always go with your console. So if your cursor is on the line where you've typed the code, you just click Control Enter, and it gives you the result. So that's how you run a code. So it's very easy. Control, you press Control, and then you hit Enter. You can click on the run option here. Maybe you've typed 15 different lines of codes, and you want to run all of them. You can always highlight all of the codes and run. Maybe you want to run a previous code, for example. You can use this other blue arrow. You can run a previous code, and so on and so forth. Maybe you've typed 1,000 lines of code, and you want to go to code number 510, but you've forgotten the position, and you don't really want to scroll right down, but you know the name of a function. Maybe on code number 510, the word mean is there. You can just come and you search. So there's a search bar. You can just search the word mean, and you run. Arrow will select all lines of code that has the word mean, so you can be able to search from there and so on. So it works like our normal Word document. It works like a normal dictionary. It works like a programming language. There are so many different functionalities. But again, you get to really familiarize yourself with this software over time. So the more you use the software, the more you just keep discovering new things and so on. That is why I keep telling you, if someone tells you they want to teach you Arrow from beginning to the end, then it's not possible, because the only way you get to understand and really get used to this software is by using it. The more you use it, the more you make errors, the more you see those error messages, the more you get familiar with it, and so on and so forth. So it's just about practicing. Now, we'll see some of these functionalities as we go through the tutorials, which is really our bone of contention at this point. So the next 1 hour, I want us to look at some very, very basic things. Again, like Jude mentioned, if there are some questions, just jot them down, or you just drop them in the chat. And towards the end, Jude will look at some of the questions, and then we go back and we answer your questions, okay? I just want to see how much we can cover within probably the next 45 or 50 minutes, and then we take the questions at the end. So, R, like I mentioned, can function as a calculator, and you can use it to do very, very complex analysis. If I tell 1 plus 3, it's like a calculator. It just gives me the answer 4. At the same time, you can plot a code that has 50, 60 different lines, or 50, 60 different functions. So R is in such a way that even a secondary school or primary school kid can be able to program using R, as well as advanced data analysts. People who work in very big organizations who analyze very, very big data can also be able to use the software. So we'll start by looking at some very basic things of vectors. So again, here we're not teaching you mathematics here, but we are using the concept of numbers to understand the programming language. Because again, like I mentioned, R is like you're learning a new language. And for you to be able to write a whole paragraph, for you to be able to do a whole analysis in R, you must first of all understand the letters of the alphabet, the very basic vocabulary, so that when you're giving those instructions to the software should understand. Because this thing has already been programmed. Programmed in the sense that anything you write and run, which is not what is already in the system, R will tell you, I don't know it. So you cannot just improvise a code and you write and say, okay, no, this code makes sense to me, it's going to give me the results. No. The only thing that gives you results in R is something that has already been incorporated into the algorithm, such that you type the code exactly the way it is. So if you type a code and you miss a full stop, you miss an inverted comma, you miss a comma, you put a wrong bracket and so on, you never get the result. So it is very, very sensitive. Another thing you have to note with this software is that it is also sensitive to spelling. So if I want to type the word mean and I forget to type the right spelling, it gives me an error. It's also case sensitive. If I type mean, if in the software, mean has been designed as MEA and lowercase, and you type mean and the M is in uppercase, I will tell you it's the same spelling, but I don't know the name. So you have to be very careful when you type in, especially from the beginning. It's case sensitive and it's very, very sensitive to capitalization and even spelling. Just the number.
Sorry for the network problems. Just let's be patient and people will reconnect with us.
Yeah, please just give me a second. Let me. Okay, my R RStudio has been open for a while now, so it's. Let me save it. Okay. Can you hear me?
Yeah, we can
right.
hear you.
Share my screen one more time. Sorry about that. Okay, are we there now?
Yeah, we can see your screen.
All right, great. So I just want us to start by looking at basic functions of vectors. Like, how can you tell arrow to write mean numbers? Like, we just want to write series of numbers. So we'll look at vectors and then we move to how you can be able to develop a matrix. But again, the essence here is not the concept of vectors. We are using the concept of vectors and matrices to understand how to code in R. How do you write a function? Where do you put a round bracket? Where do you put commas? When do you use capitalization? Where do you use equal to, and so on? That is what you should be focused on. We are not teaching you guys how to do a vector here. No, that's not the essence. But it's just we're using the concept because, again, when you're looking at a data set most often is just numbers that have been arranged in rows and columns, just like how a matrix is. So if you understand how you can be able to manipulate a matrix from those very basics, you can now be able to see how you can be able to transfer such knowledge, those ideas on a very big data set and so on. So we want to look at, so again, throughout these tutorials, we'll see some basic terminologies like a function, like an argument. So what is a function? A function in R is just like that word or that letter that is capable of giving the software a particular instruction. For example, mean. Mean in R knows that mean is used to calculate average. So the word mean is a function. And the word mean already is inside the system. So R recognizes the word mean. If I go and put the word computer, R doesn't understand what computer is. Computer is not a function because when you type computer, it doesn't give R any instruction. So a function is just that letter or a word that is capable of instructing the software to do a particular thing. Again, it could be a letter or a word, and those functions have to be written the way they are. The questions you might want to ask is, do I need to memorize all the millions of functions to be able to use this software? No. That is what I earlier mentioned, that for you to be able to master the art of programming, you must be able to practice. You cannot learn Chinese by memorizing letters and sentences. No. But the more you keep practicing on how to write sentences and words and paragraphs and practices, the more you become very effective in the Chinese language. That's exactly how the programming language works. And in just like how in a particular language, there are words that if you write them in a different way, it will not be accepted. The same thing with the programming language. The words, the functions have been designed in such a way that you have to write it the way it is for R to be able to recognize it and know that this is what you're trying to say. For example, there's a function, you don't really need to bother so much about the names of the function and all of that. What we're interested in is what the function does. This small c is a function that we call it concatenate. Now, what does this function do? If you look at this first line of code that I want to write, I type C in bracket 479. So if I run this code, it just gives me a series of numbers 479. One of the things you need to note when it comes to a function is that when you type a function, so in this case, the function is this small c. If I type this small c in caps and I run, you see, Ari gives me an error. Ari says object not interpretable. It means that this small c is a function only when it's written as small letters. And what does this small c does? Small c just tells R that print me these numbers 479 the way they are. So when I put C and then inside the bracket, I put 479 separated by commas, and it gives me the result 479. Again, after every function is followed by a round bracket, where inside the bracket now you put the arguments of the function. So if I tell R concatenate or combine, because you can also use the word combine to define that function, C. What am I combining? Inside the bracket now you put what the arguments of what you want R to combine. It's unlike for Python, for example. One of the challenges of Python is that there are so many different brackets. You can use a round bracket for a function, but we want to create a data set in order to use the curly brackets. The curly brackets also have different uses here, but in R, I think the way the brackets are being used are a bit easier as compared to Python. Another use of the concatenate function is, for example, here I concatenate 3 different arguments. 1, which is a number, true, which is a word written in capital letters, and 3 is also a word which is written in quotes. Now, when I run this, it gives me 1, true, and 3. But if you look at the way these 3 numbers are written, they are written in different ways. 1 is a number which R already knows. The word true is written in capital letters. True is a word, is not a function, so R does not know the word true. 3, R knows 3, which is a number, but R does not know the word 3. So when you're writing any word in R, which is a string or a character that is not recognized by the software or that is not a function, you put it in quotes. So when I put the word 3 in quotes, R can be able to read it without any error. The word true, if I type it in lowercase, R will not be able to recognize it. But when I type true in capital letters, true in capital letters in R is a function. It's just like accepting something. We'll see the use of this true. So these are 3 different argument types that have been written. 1, which is a numeric argument, true, which is a function, and 3 is a character. We can call it a string. So in the place of these 3, I can put my name, for example, Che, and I run. Che is not a function, but it's a name. You can put anything. You can put John. I will still be able to recognize it. But the moment I type John without the quotes, Ari tells me object John not found. Ari tells me I don't know what John is. In my system, the way I've been designed, the functions and the words they've put in my brain, John is not part of them. But if you want to convince Ari that you recognize what John is, put it in quotes and we run, Ari now prints now the result for you. So these are some of the things that you have to, but again, as we go even throughout this session, you understand more of the time. Another thing we want to look at is how can I write series of numbers? If I want to tell Ari that print me numbers from 1 to 10, for example, I just write 1 colon 10. So 1 to 10 is just a sequence of numbers. So if I write 1 colon 10, colon here stands for 2. So here the function is this colon. So if you want from 5 to 10, you just start from 5 colon 10, and I will print you a sequence of numbers from 5 to 10 inclusive. You can use another way, SEQ. SEQ here is also a function. Remember, I mentioned that after every function is followed by a bracket, a round bracket, where inside the bracket, you specify the arguments of the function. So in this case, I want to type series of numbers from 5 to 9, but I don't want to use this colon function, I want to use the sequence function, seq. I type seq in bracket from equal to 5, comma, 2 equal to 9, and I close my bracket and I run. Arrow gives me from 5 to 9. I can still do the same thing by just typing seq in bracket 5, comma, 9, and I run. It gives me the same result. So you see, these are 3 different ways of doing the same thing. It's now your choice. You can choose which one is easier for you to do. So probably these are 3 different people who have developed these 3 different codes of writing a series of numbers, either by using the colon or by using the seq function and specifying from where to where, or by using seq and separating the lower and upper limit by a comma. It gives you the same result. Now, what if I want to write this series of numbers and I repeat them? Maybe I want to tell arrow that, okay, repeat the numbers from 1 to 5. I use the rep function. I can tell arrow that repeat in bracket from 1 to 5. When I run, no, sorry, this is repeating 1 5 times. So arrow gives me 5 ones. So you're repeating 1, 5. It means repeat 1, 5 times. In the second case, I want to repeat from 1 to 3 5 times. So if I run it, it gives me 1 2 3 1 2 3 5 different times. In this other case, now I have the 3 different functions. I have the repeat function, I have the concatenate function which you saw above, and I have the sequence function. Remember, we said concatenate function is just telling you that give me the things in series, the way they are arranged. Repeat function is repeating them, and the colon is giving you a sequence. So what I'm doing here is that I'm telling R that give me the numbers from 1 to 3 and from 1 to 2 5 times. And what this small c is doing is that it's telling R that first of all give me 1 to 3, and then you give me 1 to 2 5 times. So look at the output. R gives me 1 2 3 1 2 1 2 3 1 2 1 2 3 1 2 5 different times. Now there's something very interesting here. If you remove this c and run the same code, it gives you an error. Why does it give you an error? What this small c does is that it tells, because you're telling arrow to repeat 1 to 3 and 1 to 2. If you don't put this concatenate function, arrow will not know which one to start with. So the small c is telling arrow that first of all type 1 to 3 and then type 1 to 2. But without, so by default, arrow will not decide to type 1 to 3 first. You need to specify. So this software does not do anything if you don't command it to do. There are some things that it does by default, but not basic things like this. You should be able to tell it what to do. So this concatenate means that type it in that sequence. First type 1 to 3, and then 1 to 2, and then repeat all those things 5 different times. And that is what it's doing here. Another code here, the concatenate is outside. And then we are repeating 1 to 3 5 times. When we are done, we repeat 1 to 3, 1 to 2 5 times, and then we arrange them the way they are in this concatenate bracket. So let's run this and you see. So here we have 1 2 3 1 2. This is 1 2 3 1 2 3 1 2 3 1 2 3 5 different times. When we are done, we now have 1 2 1 2 1 2 5 times. So this one we had 1 2 3 1 2 repeating 5 different times. But in this case, we are having 1 to 3 repeating 5 times, and then 1 to 2 repeating 5 times. And the reason why we have this repeating first before this is because of this function. So this function in simple terms is, take for example, I have 50 different colors and I want to share to 50 people in class here. The fact that we're sitting 1 to 50 and I have 1 to 50 different colors, and I tell R, take these 50 different colors and share to these first 50 people. By default, R will not take the first color and give to the first person. You need to tell R. Because if you don't tell R, there are n different number of ways, there are n combination of ways. R can take the first color and give to the 10th person, the second to the 20th person. So for you to instruct R to ensure that R takes the first color and gives to the first person, the second to the second, the third to the third, the fourth to the fourth, you concatenate that function. That concatenate now actually restricts R to print out the results in the sequence in which it's written in that bracket. And that's exactly what is happening here. Here, it first of all prints 1 to 3, and then 1 to 2, and then repeats it 5 times. Here, it prints 1 to 3 5 times, and then when it's done, it prints 1 to 2 5 different times. So these are some of the basic things that if you understand them, When we get to very complex codes, it's just these same things that I've been repeating over and over and over again. Now, the next thing we want to look at is just still applying this concept of vectors to create a matrix. A matrix is just numbers arranged in rows and columns. So here, instead of just writing numbers, we want to arrange these numbers in rows and columns using a function called matrix. Now, but before this, there's something that we call an object name. So take, for example, right? If I give you water and I say, take this water, if I tell you to give me 1.5 liter of water, the first thing you need to think of is to get a container, an object, which can contain 1.5 liter of water. The reason why you put that water in 1.5 liter is such that it can easily be manipulated. You can easily carry it from one place to another. But imagine you have to handle 1.5 liter of water without it being in an object. It's practically not possible. So it's the same thing with programming. Programming, you need to develop the habit of creating object names. The reason why you create object names is to be able to assign your codes to those object names to make it very easy for you to manipulate it. Now, let's take, for example, here I want to create a matrix. And the function to create a matrix is called matrix. So I tell R that I want to create a matrix, for example. I open my bracket, I define how I want my matrix to be. Remember, we said 1 colon 12 means from 1 to 12. So I want to create a matrix from 1 to 12, comma. And we says, okay, the next argument is the number of rows of my matrix. I say n row, number of row is equal to 3. Again, this is also a function. And then by row equals to true. I will explain to you what by row equals to true means. This true means that yes, by row equals to true is like saying by row equals yes. So this true is written like this. Arrow recognizes it because it's a function. You can also put false if you don't want it to be by row. So if I run this code, automatically it gives me this matrix from 1 to 12 with 3 rows, 1, 2, 3, and I refuse a number by their rows. By their row means that it fills 1, 2, 3, 4. So it fills from left to right. If I put by row equals false, it will fill from top to bottom. But now, if I have to use this matrix subsequently, it means that each time I want to use this matrix, I have to come and copy this long code and I paste somewhere to do whatever I want to do with it. But to ease my life, what I can do is that I can now take this matrix, which is like my 1.5 liter of water, and I put it in an object. I put it in a container such that I can easily manipulate it. So I can give my container a name. You can give it any name. It could be X, it could be Y. But most often I choose to give it a name that is like a representation of my code. So in this case, since I'm designing a matrix, I just choose to give my object name my.matrix. And then I assign, this assign is just like equal to. In Python, you mostly use equal to, but in R, you use the assigning function, which is a less than and hyphen. You see the less than a hyphen is like an arrow pointing to the left. It means that this code on the right has been assigned to this object name on the left. So if I run it now, automatically this code has been assigned to this name. So if I want to see this result now, subsequently, all I just need to do is I run the name my.mat. So if I want to do anything on this matrix, I don't need to come and type this wrong thing again. All I need to do is my.mat. Again, this is just my name that I choose. You can put your name there, but always try to give a name that is very easy for you to remember. I can decide to assign it as X, Y, Z, or whatever object that I choose to. How important is this? If I have to transpose this matrix, for example, let's say I want the rows to become columns. I just give another object name, for example, and I assign it. This small t is the function that we use to transpose. So what am I transposing? I'm transposing this matrix. But this matrix had been assigned to this name. So inside the bracket, instead of copying this long code and pasting in this bracket, I just put this name my.mat. And when I run, and I ask arrow, what is this new object? It's now the transpose. So now we have two matrices. We have the first matrix, which is this name, which is this, and then we are transposed this using this small t, which is also a function, to this other name called my.mat2. So these are two different matrices. This issue of object name can make your life very easy. It might look very easy now, but imagine you're working on an analysis that you have to run like 5,000 or even 300 to 500 lines of code. If you don't assign object names, you get so confused because you run a long line of code, but it's possible to just assign that long code to a simple name such that subsequently, if you want to use that same result to do another analysis, it's just that short name that you're introducing. You don't necessarily need to type the long thing. It's just like taking your water, put in a container, and with that, you can now be able to carry that water along and do so many things, put color, change a lot of things in it, and so on. You can look at the dimension of your matrix using the DIM function. You can look at the number of rows, for example. What is the dimension? A row tells me it's a 3x4, 3 rows, 4 columns. What are the number of rows? 3. What are the number of columns? There are 4 columns, and so on. You can want to index. What does indexing mean? Indexing is like, okay, if I tell you, or if I ask you that, what is the number on the first row and the third column in my transpose? So this is the transpose on my matrix. So I tell Arrow that go to my transpose, which is this name. Now we are not using the round bracket, we're using the square bracket. So the square bracket is used to index. If I say what is the number on the first row, third column, this is row 1, column 3, which is 9. The reason why you can say it's 9 is because this matrix is very small. Imagine I had a matrix of 50 rows, 120 columns. And I ask you, what is the number on row 30, column 119? You'll not be able to scroll through and tell me. All you just need to do is that you put the name of your matrix, square bracket, the row number, comma, the column number, and you close your bracket. So the indexing rule states that in the square bracket, the first number represents the rows, the second number represents the column. So if I want the number on row 1, column 3 of my transpose, which is this name, remember, I'm now just using this name because I assign it here. I just run and it gives me 9. I can want the number on row 2, column 2. It gives me 6 and so on. You can change it whatever, how you want it to be, and so on and so forth. So there are a lot of things you can do with this matrix, but these are some basic things. You need to be able to understand this issue of object names is very, very important. In every programming language that you use, whether Python, R, it's always important to assign object names. Even in mathematics, where you have f of x is equals to a long code, a long equation, and then f of y is the same thing. So that each time you see f of x, you know f of x represents that long code or equation, and f of y represents the other equation, and so on. It's the same thing we're trying to do here. Here we're assigning our code to an object name. We'll see other instances as we move down. Now, the next thing we want to look at is installing packages. Remember I mentioned that when you want to do specific analysis, there are functions that these functions have been put in packages. Packages are just like folders that have been arranged online with different functions that helps you to do analysis. Here we want to clean data. So we have some data sets that we import and do some data cleaning. But for us to be able to effectively clean our data, we need to install some packages, the dplyr and the tidyverse package, or the tidyr. So how to install a package? You just need to know the name of the package, and you type install the packages in bracket, you put the name of the package, and you run. Here you need to be connected to the internet. And when you have installed the package, you just need now to load it from the library so that you can now be able to use it. I don't need to install the package again because I already have it. I just put the code here for explanation purposes. So when you install the package, you see it downloads from the internet when you're connected, and then you load it from the library. You can now be able to, so there are so many different functions found in these two packages that we can use to clean data. This is also another package that is used if you want to import an Excel file. I'll show you how to import different file types. If you want to import an Excel file in R, you need to install this package called read Excel. The question you might want to ask is, how do I know that this particular analysis requires a package? That is where practice comes in. The more you practice, if you see a tutorial online and they are trying to do maybe a t-test or a regression, if it requires a particular package, they'll mention it there. You just need to type install the packages and you put the name of the package in quotes. You download it from the internet and you can now be able to proceed. So we now have these two packages installed. Now I want to import a data set. One of the very important things that you need to do to import a data set is you need to set a directory. What does it mean? Imagine that we are in a room, we're in a house which has 10 different rooms. And I'm in the sitting room, for example. And I ask you, I want you to go to room number 10, go to the shelf, or there's a data set in the cupboard of room number 10, and I want to bring it to the sitting room where I have to analyze it. Because there are so many different rooms, and in those rooms, there are so many different data sets, I need to be able to direct arrow to the particular room. Rooms here mean folders in my computer. I need to be able to direct arrow to the particular folder where I have this data set. That is why if you're interested in data analysis, you have to be well organized. Folders, your documents have to be arranged in folders. If not, you're going to mess up your life, because you need to be able to arrange folders so you can be able to set a directory to a particular folder where you want Array to import a data set. There are different ways of setting directory, but I'll show you one of the easiest ways that you can use to set a directory. For example, there's a data set in my computer that I want to import, which I want to use for data analysis, for cleaning. I decide to set this directory. I go to session. Remember I said there's an option called session up here. If I click on session and I go to set working directory and I scroll down and I choose directory, it takes me into my computer. So I'm in my computer. So where is the folder? I select the folder. So I select the folder, for example. So I'm in this folder. So this is the folder. So I already know where I save the data. So I'm in this folder. When you get into the folder, it shows empty. It means you're inside the folder because you've not decided the data set you want to import. So when I click on open, you see that there's a directory that has been set. This directory is showing me where my data is. Now I have set my directory. It means that I've instructed Array that go into this folder. Array says, okay, I'm in this folder. Array confirms that I'm in the folder. The next thing you want to do now is to import the data set that is found in that folder. Maybe in that folder you have like 10 different data sets. You want to import just one of them. So if you need to know the name of the data set you want to import. Of course, you can always go back to the folder and confirm the name in terms of spelling and all of that. The first thing I want to do is to import a particular folder, a particular data set. Now, how you import a data set is based on the file type. Is it an Excel sheet? Is it a CSV? Is it a SAS file? Is it an SPSS file? And so on. I'll show you how to import CSV and Excel files. CSV is just like, it's a type of Excel sheet. It's just a file that is separated by commas. Most often, programming languages really feel comfortable with using CSVs. Most of my data set, even when someone sends me an Excel sheet, I always convert it to a CSV before using it because it's easy. I don't need to install a package like here. CSV is very easy. And the function to import a CSV file is read.csv. So if I take read.csv, which is a function, the bracket opens. I now open my bracket. What is inside the quotes in the bracket? Now I type the name of the data that I want to install, I want to import. So this is the name of the data that I want to import in my CSV. And I put the .csv because, again, you might have other file types with this name. So I put the name of the data .csv in my data set, in my code, and then header is equal to T. T means true. It's the same way as writing full true. I'll explain to you what this means. So if I run this, it gives me the data set. So this is the data set that has appeared here. But again, there's something that I mentioned a couple of minutes ago about creating an object. This data, it's easiest for us to just create an object. So let me just give an object name herbivore, for example, and I assign it to this. So this code has been assigned to this name. So it means if I want the output of this code, I can now tell Arrow that view, I want to view, instead of viewing all of this code, I just type view herbivore and I run. So this is my data set. So I've used the read.csv function and I've imported this data. I've assigned it to this name, and now I want to view the data. So when you view the data, it appears like an Excel sheet. So this is the data that I've imported. It's a data of like 100 entries and 11 different columns and so on. Again, this header is equal to true means that you're just telling R that consider all the first entries, the first row as headings. That's what the header equals to true means. Because again, when you're importing data, when you're keying your data on Excel, the first row is usually heading. So that's what header is equal to true means, that all the first entries should be considered as headers. That's why you see Array starts reading the data from the second row, which is from here. The first row is considered as the heading. That's what header is equal to true mean. So as I've imported this data, I can do a summary statistics, right? I can look at the summary of the data. So if I want to summarize now, I'm now summarizing herbivore because the name of the data I've imported, I've given name herbivore. It's just my choice of name. You can choose any object name here. So I can summary in bracket herbivore, So when you type summary herbivore, it gives you a summary statistics of your data set. Every variable, for example, it takes this variable called replicate. It gives you the minimum value, the first quartile, the median, the mean, the third quartile, the maximum value. So you don't need to, so with this, you already have an idea of the kind of data set you have. It even tells you whether they are missing values and so on. So you can, for example, if I want to know mass, the mean mass of my data, I just type summary in bracket my data. I see that the mean mass is 27.23. The minimum is this, the maximum is this, the median. So every numeric variable arrow gives you a summary statistics of it. It's very, very important. You can always do a summary statistics. Maybe I want to just calculate the mean of a particular variable. I can calculate mean of, I go to my data set. Now, how can I select one variable in that data set? I use what we call the dollar sign. The dollar sign in R is used to select a variable in a data set. So if I type the name of my data, so this is my data, and I want to select mass. I don't want to select everything. I want to select just mass. I come and tell R that select, go to my data, dollar sign. You see when you type dollar sign, all the variables form a drop-down box. You can now just select mass from there. So in this code, I want to look at the mean of just mass. And when I run, it gives me 27.23, which is the same as what we saw up there. We can look at the standard deviation of mass, for example. Standard deviation, the function is SD. So I can tell what is the standard deviation of herbivore dollar sign mass. SD, you select mass. So dollar sign again, just like how in matrices we use the square bracket to subset, in a data frame we use the dollar sign because the dollar sign will select a particular variable that you use. We'll use this dollar sign right through to the end. You can look at so many other things. Again, the summary, we can look at the structure of your data. How is there a structure? You can use the str function. Structure of the data just gives you, okay, it tells you that it's a data frame of 100 observations, 11 variables. And then it subsets each of the variable. It tells you habitat is a character variable, day, night is character, replicate is an integer, mass is a numeric variable. These other ones are all integers and so on. So when you import the data, these are some of the first things. These are some of the first summary statistics that you do. You look at the mean, the median, the first quartile, the third quartile, and so on and so forth, the structure of the data. So you have an understanding of what the data actually looks like. Is it actually what you collected from the field or what they collected from the field and sent to you, or they've made some mistakes and so on? Like I mentioned, when you look at the summary, if there's any variable with a missing value, you indicate here there are no missing values. So that is why you see you show any variable, any variable that has a missing value, it actually indicates that to you. Now, the first function we want to use is what we call the mutate function. Now, what does mutate function do? Mutate is just like changing something. For example, maybe you've collected this data and there's this variable called mass. Let's say you want to transform this. For those of you who have versed with statistics, you know that one of the ways of normalizing your data is to transform it. Maybe you want to do this, do an analysis on this mass, and it's not normally distributed, and you want to transform it using log transformation. How do you do that? How can you calculate the log of this variable mass? You can use the mutate function. You can use the mutate function. So I just simply tell R that mutate in my herbivore data. Again, it's herbivore, not herbivores. In my herbivore data, I want to create a new variable called log mass. This is just my new name that I want to put, which is equal to the logarithm. This is natural log. This is like lean. In R, log without any base is lean. If you want to calculate log to the base 10, you type log 10. So normal log is lean. This is normal log is like lean. So this is natural log of mass. So if I run this code, and I tell R that what is, and I go to my data, I scroll to the right, you see that there's a new variable that is log underscore mass. So what R has done is that R has taken this variable mass and has calculated natural log of it and put all the answers under this new variable called log underscore mass. So it means that if I was analyzing this, if I wanted to do maybe a regression, I can now use this transform variable to do my regression analysis without any problem. Again, the original mass is left. Remove equals false. Remove equals false means do not remove this original mass. Take this variable, transform it, but again, still maintain this one. So we have the original untransformed mass, and then we have the variable, the log transform variable of the log transform variable that we've created. So this mutate function is a very important function because you always see the need to mutate. You can mutate using natural log, you can mutate using square root, using square, using cube root, based on what you're doing and so on. You always use the mutate function. And again, remember the object name. Here we're maintaining the same object name because it's the same data set. We don't want to change the name of the data. It's like you're taking the same data set, you clean it, and you give it the same name. So you're taking the data set, you clean it, and you give it the same name. So you don't change the name of the data set. Another thing you might want to do is, okay, maybe this variable called mass, you imported the data, you put on R and you discovered, okay, this was supposed to be biomass and not mass. Would you go back to your Excel sheet, change it, and then you import it again? No, you just come to R and say, okay, I want to rename in my data set, I want to create a new variable called biomass and replace it with mass. So if you run it, what arrow does is that it takes this variable called mass and replace it. What am I doing? No, herbivore. So arrow now replaces mass with biomass. So you've just used the rename. So this is the function that is doing the magic. What are you renaming? In our data set, the variable mass, you rename it to biomass. So biomass now has taken the position of mass, and our data set, we have a new data set, which is now has been cleaned with this variable called biomass. Again, we have another variable, which is the unite, just like how you can unite columns. For example, look at this data set. Maybe you collect this data set and you discover that, okay, these two variables, habitat, day, night, were supposed to be one variable. But maybe the person who keyed in the data put it as two. So what do? You can merge it. You can unite it, right? So I can decide and tell R that, okay, I want to unite in my data set. This is the name of my data set, herbivore. Again, it's herbivore, not herbivores. And I want to create a new name called this. This is just a new object name a new variable name that I've created. So what am I uniting? I'm uniting a concatenation of habitat, this one, this variable name, and day, night, this one. I want to separate them by an underscore. So, sorry, I want to separate them by a /. So let me run this and you see something. So if I view, so this is what I'm doing. So what I've done is I've taken this variable, habitat and day, night, and I've united the both of them, separated by /. So what arrow does is that it takes this first name, takes this one and unite them. Take this and this, unite them by a /. And that is what this code is doing. So I'm going to this data, I create a new variable name, and this is the new name here, which is a combination of this and this. But each of the values, I separate them by this. I can also separate by anything, by a hyphen, by an underscore, by backward slash, and so on. It's just a choice. You may want to separate it by a space. You just put a space here, but you always need to specify how you want arrow to separate them, to unite them. And if you can unite two names, two characters, it means you can also separate them. So I can also come here, I take this name. Maybe this name is a scientific name. Maybe this is a scientific name, for example. Maybe initially I want to split this data in such a way that arrow comes and splits it anywhere it sees underscore, it splits it in the middle into two different columns. And that is what I want to do here. So I can tell R that, okay, I want to, so this is the function I use to separate. Just like how you use this function to unite, I use this function to separate. So I want to separate in my data set this variable called habitat. So this is the variable I want to separate. This is it here. I want to separate into two separate variables called genus and species. And I want to separate it where I see an underscore. So what arrow does is arrow will come here. Anywhere it sees an underscore, you separate in the middle and put them under genus and species. So if I run this and I view my data, so what arrow has done is that arrow has taken this habitat Anywhere it saw it sees an underscore, it separates it, takes the first, assigns under genus, takes the second, and assigns under species. And what instructs arrow to assign the first name under genus and the second under species is this small c. Because you see, in this small c, we have genus comes first and species comes first. It simply means that take the first name under this and put under genus, take the second name under species. Again, they are arranged in the sequence in which they are. Boils down to the small c we saw up there. Without this small c, arrow will not know if is the first name going to genus or is going to species. So with this concatenate here, it specifies that takes this first name to genus and the second name to the species name. Very, very important. You can also import another data. So in this same folder, there's another data called bats. Let me import it. Let me create an object name. So let me just quickly import this one with .csv. Bats underscore data .csv. So if I view bats, so this is another data set that we're just using for, again, study purposes. Here we might want to filter. So take, for example, you have a data set and you want to select all participants that have entries that are not equal to 0. For example, in this data, there is a variable called foraging. This data has 173 entries. I want to tell arrow that go into this data, go under this variable. Any entry that is not equal to 0, remove it. Remove any entry that is, keep entries that are not equal to 0. It means any entry that is 0, you remove it. So what I tell arrow, I use this filter function. So I tell arrow that go and filter in my bats data under the variable foraging. This could be like maybe you're a teacher or you have data of students. Maybe you want any student that has a score of 0, remove the student from the list and maintain only students who pass the exam. So for example, who has 10 and above. I say go under foraging, not equal to in R is exclamation sign equal to. So this is not equal to 0. So it means that anything that is not equal to 0, arrow will filter them out and assign it to this new name. So if I run this and I view, yeah.
Go ahead, Mr. Desmond. I think it's just a mistake.
Okay. So if I run this, see what I have. This is the original data set. You see, we had entries that had 0. But what I've told arrow is that go to this foraging variable and any entry that is not equal to 0, filter it and assign it to this name. So it's like I'm creating a subset of the data set of only entries that are not equal to 0 and give it this name. And this is it. So you see, my entries have changed from 173 to 123. It means we had 50 entries that had the value 0. So this is a very, very powerful entry because you can use this to filter. Maybe you're doing an epidemiological study and you want to filter out all participants who have age less than 5. And you have 50,000 entries. You just need to filter. Just say, I'll go under age, any entry that has age less than 5, you filter out the whole of that row. I will filter it out to you and leave only the ones that have ages greater than 5. So you can use different filter commands here. You could put greater than, less than. So if I want greater than or equal to, or I can put less than or equal to, I can put identically equal to, and so on and so forth. So you can put in as many different commands there as possible. The same way, I can do another filtering here. Maybe in this case, this is where we are filtering numbers. Greater than, less than is where we are filtering numbers. But imagine you want to filter based on a word. For example, here, these are words. You cannot say greater than medium term, less than medium term, right? So imagine here we have medium term, short term. So if I would tell arrow that go and filter out all participants that have medium term, how am I going to do that? It's still very easy. I still tell arrow, maybe I create a different object name for that. I tell arrow, go and filter in my data set, go under this variable. They need to be a particular variable that you're using as reference. So I tell arrow, go under this variable. This is the variable, treatment thing. Select all entries that are double equal to means identically equal to. Select all participants that are identical equal to short term. So arrow will come here and scans through any entry that is equal to identical to short term R filters it out and gives me this result for region 1. So you see, only entries that have short term have been filtered out. So you see that you can have a very big data and you can filter out even 10 different times based on different criteria, and you analyze them separately. You don't need to go to your Excel sheet and you start separating things. You can just use this filter function and you fit in certain criteria. You can decide to analyze only males. You can filter out only females. You can filter out only those who are primary, secondary, or tertiary education. You can filter out only those who are positive. You can filter out only those who have particular ages and so on. And you assign them to a new name and you analyze that separately. All of that we're doing is on the same script. So you see that you can have one script where you have like 15 different data sets you're analyzing at the same time. You imported one data and then you create subsets of the different data. You can filter out different subsets of the data based on particular criteria, and you're analyzing all of them simultaneously. This still boils down to the fact that creating object name is very important, because you see that this criteria, I gave it a different object name. This one, I gave it object batch of origin 1. So I have my original data set with the same name, with the name. I have this filter data set that do not have zeros with this name. And I have another data set that have only short term with this name. And I want to filter based on other criteria. So I don't interfere, because if I use the same object name here and here, it means that I will override this one. It's that you're using the same name and you give to two different things. I will forget about the previous one and consider just the present one. So you need to, if you're changing your data completely, you need to always change the object name. It's very, very important. Okay, so there are so many different functions, but again, we've seen some very important ones. Another thing I want to show you is, now, there are different ways of exploring your data. You can do descriptive statistics, like what we showed. You can look at mean, median, mode, standard deviation, and so on and so forth, as well as you can also explore your data graphically. So you can decide to explore your data as a form of a bar chart to see how, okay, the trend of your data, scatter plots, and so on. And what type of graph you plot is based on what type of variable do you have. If you have maybe a categorical variable, you might want to present in form of a bar chart to see, okay, which frequencies are more. If you have continuous variables, you might want to look at correlation to see whether there's an increase or decrease using scatter plots, etc., etc. And there's a package that you use to plot graphs called ggplot2. It's a very, very popular package. So if you have to plot graphs anytime, you just install this package. And one thing about packages is that you install a package just once. So all these packages are already installed because I've used them several times. So each time you want to use this package, you just run the library. And for you to run the library, you don't need to be connected to the internet. That is why I said, if you're going to maybe for a field work and you want to use your computer analysis, you can just decide to install all your packages before going. When you're there, you want to use it, you just run the library and you can use it without any problem. But to install for the first time, you need to connect to the internet. But later on, if you want to use it again, you just load it from the R library. This library that I showed you down here, I told you there's a library of packages down here. So you can load it from this R library, and to do that, you don't need to be connected to the internet. All right. So to do that, there is also, now there's a data set that I want us to use to plot graphs, which is called empty cars. This data set, previously we've been importing data set from external sources from our computer, Excel, CSV, and so on. But now this data set is a data set in R. So there's no excuse. You cannot say, I don't have a data set to practice on. There are a lot of data sets that have been put into the software that you can use. Now, how can you know data sets are in R? If I just type data and I run, these are different data sets that are in this software. To the left are the names of data set, and to the right are example, a description of data. For example, this data called air passengers is a monthly airline passenger numbers from 1949 to 1960. You can see carbon dioxide data. So it has data of different or from different fields of study. Johnson & Johnson, earnings per year, juvenile, cancer, those who are into economics, and so on. There are so many attitudes, so many different data sets, like euro, conversion rates of euro currency, those who are into finance, and so on and so forth. So there are so many different data sets. You can always come and check out here, import the data from R. You don't need to have the data set. It's already inbuilt and you can proceed with it. So there's a data set you call empty cars amongst this list. If I want to import it, I just type view in bracket empty car. This is the name of the data set. And when I run
the data set just appears. I don't need to set any directory. I don't need to use any read.csv. I just tell that I want to view that data. Since the data is already installed in the software, it just appears and I can proceed with it. So this data is a data of different cars, Mazda, and so on. There are different speeds, and it was recorded, and so on and so forth. Probably they were testing different cars, Mercedes, and all of that. We just want to use this data to do something. We are not really analyzing the data because we are not the ones who collected it. So you can see different gears and the different velocities of the cars, the different carbon dioxide emissions, and so on and so forth. Now, we want to plot we want to create a frequency distribution table. Like we want to take a variable that is categorical and we count how many of this category are there and so on. So in this data, there are two variables that we want to categorize, we want to count. This variable called VS and this variable called gear. If you see VS is coded as zeros and ones, so it's categorical. Gear is coded as 3, 4, and 5. So there are two categorical variables, but it's just that they have been coded in numbers. So 0 here could be low velocity, 1 could be high, and then gear 3, 4, and 5, and so on. So I want to create a table of, remember I said $sign is used to select a particular variable. So I want to create a table of this velocity and gear, and I assign the name of that table to count 2, for example. So if I run this table, and I ask R, what is count 2? R gives me, this is count 2. So this is gear 3, 4, and 5, this is 0 and 1. So these are the frequencies, 12 for 0 and 3, 2 for 0 and 4. So this is like a 2 by 3 table. So this is a frequency distribution table for these two variables. But now, if I proceed to plot a graph like this, you might not really appreciate it because we don't know what 0 and 1 stands for. We don't know what 3, 4, and 5 stands for, right? So because we are not the one who imported this data set. So for explanatory purposes, I want us to rename these rows and columns. I want us to rename 0 and 1 as positive and negative, and 3, 4, and 5 as primary, secondary, tertiary, for example. How do we do that? It's very easy. I just tell R that go to the row names of my table and replace it with positive and negative. Again, this is our magic C. What does magic C tell us? That take the first row assigned to positive and the second to negative. If you don't put this C here, R will go to the row names, but it will not know which one should be given positive and negative. But with this small C, you're telling R that rename them the way they are arranged like this. The same way, go to the color names and assign primary, secondary, and tertiary to 3, 4, and 5. So if I run these two codes, and now I check what my table is, you see my table now has positive and negative as the row names and primary, secondary, and tertiary. I can decide to say, okay, I don't want to plot the frequencies. I want to plot the percentages. And what is percentage? Percentage is just number divided by the sum times 100. So I just fit in the formula. I say, okay, I want to change this my table to the frequency divided by the sum of the frequency times 100. So if I run it and I ask R, okay, what is the output? So R has calculated the percentages for me. It has taken 12 divided by total times 100, and these are the percentages. So I can now plot a bar plot, for example, of maybe positive. Let's say this is HIV prevalence versus level of education. So I want to see whether maybe the number of positives that have primary, secondary, and tertiary graphically, for example. And the function to do a bar plot is very easy. You just tell R that I want to plot a bar plot. Now you see it's getting tricky now because we have a lot of functions that we want to, a lot of commands, a lot of arguments that are fitting in. The first thing is that we want to plot a bar plot of this count 2, which is this our table. What is the next thing? We want to add the main. In a plot, the main is the heading. So we want the graph to have the heading equal to maybe education versus prevalence. We put it in quotes, we have assigned the heading to our graph. The next thing we want to assign to our graph is the legend, or like the key. So the legend is our row names of the count 2. So we want to consider the row names to be our legend. And we want to put the legend on the top right, Beside equals true. We want the bars to be side by side. We don't want them to be stacked bars. Color, since there are two outcomes, positive and negative, we'll assign red to positive and blue to negative. We have concatenated two different colors, comma. We label the x-axis using the xlab function. X label is equal to level of education, and the y label is percentages. So with this, if we plot a graph, we'll have something like this. Now there's something, right? When you plot a graph and then it tells you, it gives you this error that figure margin is too large. What does that mean? It simply means that this window is too small for the graph to fit inside. And the reason why we're having this is because I've zoomed out my screen. So my screen is now bigger, and then the graph is too big to fit into this margin. So what I can do is I can zoom out so that it gets smaller a little, and then I run the code, and now I have my graph. So each time you run a code and you have this error, you don't feel like your code is wrong. Figure margin is too large simply means that the margin of the graph is too large that it cannot fit here. And most often it's either because this window is too small, or maybe you've zoomed out your screen too large, and then the graph now it becomes bigger than the margin, than this space. So this is a graph. It looks beautiful for a start. Again, there's a lot we can do on this graph. Let me zoom it so you can zoom it here. So when you look at this graph, you see the color intensity and everything. You see the heading, the legend, positive and negative. It corresponds to positive and negative, primary, secondary, tertiary, the percentages. We have our heading and so on and so forth. So you can always customize as much as you can. You can extend this label because, of course, it doesn't make sense that the bar is longer. You can extend this axis maybe from 0 to maybe 50 and so on and so forth. You can put error bars and all of that. So you can customize your graph. The difference is that when it comes to plots, everything that you want to add to your plot, you must put a code. There is a code for it. So you can plot a plot with as maybe even 50 different lines of code based on so many things that you want to add. You can customize your plot as much as you can. Now, we'll see some more functions on customizing. So there's another data set that I want us to import. Let me send my directory. It's in a different folder in my computer. So let me just open that.
So Mr. Desmond, we have used 1 hour, 30 minutes.
Okay.
So, but I have given you 30 minutes more. Would that be enough?
Yeah, I'll round up before then. So I think in the next 10 minutes, we should round up.
Okay.
Yeah.
But if the participants want, and then because we'll have a question and answer session, so yeah, you can round up, and then if they have questions, please note them down, and then we'll take the questions.
Okay, no problem. So let me just round off. We have some few statistical tests that I want us to look at. Then I think that's it. So here we have, so I've imported this data. This is a different data that I've imported. And I want us to plot a variable of height versus temperature. Height is a continuous variable. If you see here, there is height. There's a variable called height, log height, and temperature. So this is log height, which there are two numeric variables. So we want to plot a scatter plot to see the correlation and so on. Again, you specify the data, the X label, the main, which is the heading. cx.lab, this is also a very important. cx.lab now is the size. So maybe you want to change the font size of your graph. You use this function. So font size scale in R is not like that we use in PowerPoint and Excel, where you have 2, 4, 6, 8, and so on. The font size here varies by 0.1. So this is the font size. So cx.label means you want the font size of your labels of your graph to be 1.2, and you want the font size of the axis to be 1.5. You can always vary it based on how large you want it to be. And you want your points on your graph to be red, the X label to be this, PCH equals 16. I will explain to you when I show you the image of the graph. And then you want the X limit to be from as the axis of the X axis. The limit of the X axis to be from -10 to 30. If you want to change the Y axis, you just put Y lim and you concatenate the lower and the upper limit. So if I run this code, it gives me a graph that looks like this. So we have our main. So you see our X label is from -10 to 30, our X limit, our Y label, and we have our graph and so on. So again, you can customize your graph as much as you can. It's just about what you want. With graph, I can plot this graph and I choose, instead of putting red, and I choose maybe blue. You see, it changes to blue. Instead of using blue, I use pink and so on and so forth. You can add a line of base fit, an AB line, and so on and so forth to have a scatter plot. If you see that maybe there are some points that are way out of the scale, you might stretch the scale of your axis by using the X limit function. You might also stretch the scale of your Y axis by using the Y limit function and so on. You can increase the font size and so on and so forth. You can customize your graph as much as you can. And lastly, I want us to look at a few statistical tests like t-test. I'm sure some of you are anxious to see that. So there's this data set. Okay, so let's say we want to do a t-test. We know we use a t-test to compare the mean between two groups, for example. Let's say we have gestational age and sex. We want to see whether children who are born with low birth weight, we want to see whether maybe their low birth weight, their gestational age is influenced by their sex, for example. Whether the age at which a child is born is influenced by the sex using a two-sample t-test. So we have this data that we've imported, which is VB. And we have age, you see there's sex, male, female. And then we have gestational age, which is a continuous variable, 35 weeks, and so on and so forth. So we want to see whether, based using a two-sample t-test, whether the gestational age can be influenced by the sex. So the first thing we do is that we subset the gestational age of females. We tell R that go to the gestational age and select all sexes that are identically equal to female. The same thing, go to the gestational age and select the gestational age of all sexes that are identically equal to male. So we now have the gestational age of males called age female or female, and then we have that of males called age underscore male. So now we can now do a t-test. To do a t-test is very easy. One of the easiest things to do in R are statistical tests, because you don't need to write very long line of codes and play around with a lot of things like what we do in plots and so on. It's very easy. So we now have two gestational ages, that for females and that for males, and we want to compare to see whether the gestational age, there's a significant difference between the gestational ages of these two groups. We use a t-test. So we assign an object to our test, and the function that we use to do a t-test is t.test. So we tell R that we want to do a t-test between gestational age of females and gestational age of males. Now, alternative is equal to two-sided. What does this mean? What is our hypothesis? Are we testing whether there's a difference in the gestational age, or whether the gestational age of males is greater than that of females? Alternative is equal to two-sided means that if the gestational age of females is less than that of males, I will consider it. If it is greater than, I will consider it. So I is looking at a two-sided comparison. You can also be doing an analysis where you want to see whether is the gestational age of females significantly less than that of male only. If it's greater than that of male, I does not consider it. So the alternative equals two-sided means that you're considering whether is it less than or is greater than that of males. So you're comparing on both sides, whether which of them, whether it's different from. So two-sided means you're looking at whether there's any significant difference, whether greater than or less than. So if I run this code and I ask R what is my result, it gives me a very simple result here. So we have the data, it tells me it's a wedge two-sample t-test, the data, the t-statistic value of 0.79, the degree of freedom, a p-value of 0.4292, and then R returns a alternative hypothesis that the true difference in the means is not equal to 0. And then it gives us the confidence interval, and it now prints out the mean of X. So the mean gestational age of females is 29, and that of males is 28.8. So you see that there's a difference, true, of around 0.0 something, but the difference is not significant, and it's confirmed by our p-value. So here it's very easy because R gives you all the results. You don't need to do any extra thing. It gives you the p-value, it even returns to you the alternative hypothesis, it gives you the t-statistic value, gives you the confidence interval, and then gives you the mean of the two gestational ages, compares them, and tells you whether there's a significant difference or not. You just need to fit in your two variables here, the two variables that you're trying to compare, gestational age of females, age of males, and you specify whether you want to check whether there's a difference or not, or is it less than or greater than, So when you specify two-sided, it means you're checking whether there's any significant difference, whether less than or greater than an array prints out the result for you. So it means that in this data, here we cannot say gestational age is influenced by sex. So it means that the age at which a child is born in this study is irrespective of their gender. Whether you're male or female, it does not influence how long you stay in your mother's womb before you're born. That is exactly what this result is saying. Because we've seen that the mean gestational age, there's no difference, there's a difference in the mean gestational age, but that difference is not significant enough. Because a female child is born on 28, this is the average 29, males are 28.8. So you see that there's no significant difference. So your gestational age is irrespective of gender. That is exactly what this result is telling us. We can as well do a one sample t-test, which is even easier than this, where we just compare to a hypothesized value. We can do a chi-square test. Chi-square test here, we're just looking at, okay, whether there's a particular variable is independent or dependent of another one. So we can create a table of maybe we want to look at twins. There's a variable here called twin status, 0 and 1, not twin, and sex. So we want to see whether your twin status is dependent or independent of sex. We create a frequency distribution table, male and female, not twin and twin. And then we do a chi-square test. So this is all about chi-square test. But before you do a chi-square test, of course, there are assumptions that you have to test, right? You chi-square.test, this is the function. You want to do a chi-square test between twin and sex. So we want to see whether these two variables are independent of each other. So if I run it and I ask arrow what is my result, arrow tells me a p-value of 0.7, a chi-square value of 0.14, 0 freedom 1. It tells me that these are two independent variables. It means that twin status is independent of your sex. So your sex has nothing to do with your twin status according to this data set. So to do a chi-square test, you just create your frequency table and then you feed that results in a chi-square.test function and you can run. Again, in R, if there's something you doubt, you can just go online, how to do a chi-square test in R. And you see a very short code tutorials, you can just copy and you do the same thing. And the last thing I want to show you is a regression model. In this data, we have a variable called level of education of mother. So this data is looking at boarding school versus day school children and those who are obese and not. And one of the factors that they consider here is the level of education of the mother. Maybe children who come from homes where the mother are well educated, they can take good care of them, feed them very well, and so on and so forth. So in the same data, we just want to rename this data, this variable, to edu of mother. And then we can also mutate because body mass index is our outcome that we want to see whether it is correct. We want to see the regression with. So we check for normality. If it's not, we can transform it again using this mutate function that I showed you earlier. So we can log transform it and we can plot a histogram. We can check and so on and so forth. We can slice. Maybe the data is too big. We want to analyze maybe just the first 100, first 500 entries. We can also check all of that and so on. I have an error somewhere. So on here, okay. So let me. So now there's a folder where I save the data set. I'm just trying to figure it out. Just give me a second. Where's the save lesson for me? Okay, let me just explain to you what we're doing here. So I can't find the folder again. Probably I just need some time to figure it out. So we import this power data. So this is also another data set that we import, and you can, again, before you do a regression model, you need to check your outcome variable, whether it's normally distributed. If it's not, you can transform it using the log, like we showed earlier, and so on and so forth. And you can go ahead to do a simple multiple linear regression model. For example, the first code here is doing a simple linear regression model where BMI, body mass index, is our outcome. I want to do a regression with weight. So LM is the function. LM stands for linear model. So LM is the function that we use to do a regression model. So we want to do a linear model between body mass index and weight to see whether there is maybe a significant association between weight and body mass index. But now if you want to do a multiple linear regression model means that you can factor in more than one independent variable. So in this case, instead of just looking at correlation or association between body mass index and weight, you can look at weight and height as well. So you want to see how weight affects body mass index when the height also is taken into consideration. You might also add maybe abdominal perimeter, you might add systolic blood pressure, you might add diastolic blood pressure, and so on. So you want to see how maybe several variables at the same time are affecting your body mass index, which again, this is the best case because you cannot say weight is the only predictor of body mass index, but there are so many other things that are involved. So ideally, when you have a data set, fitting in a multiple linear regression model is best because with that, it takes into consideration all the different risk factors or all the different predictors that can be able to affect your outcome or your dependent variable at a particular point in time, all right? Okay, so I know that was very quick, but again, there's so much that we can do, but again, due to time, this is the little tutorial that I prepared for you guys. It's just about practice. It's just about trying to be able to see how much you can be able to do when you have the time. Again, I always say, if you can practice 30 minutes a day on coding, you're better off than someone who sits 6 hours in 1 week to practice. Because the more you practice, the more you keep making these errors, and you can now be able to identify and so on and so forth. All right. So that said, there's just so much we can do. So we, like Jude earlier mentioned from the beginning, we offer this training that we do.
Please just go ahead and share your slide, Mr. Desmond, and show this.
It's not shared.
Yeah, just share the PowerPoint again.
Okay.
While he's doing that, if you have a question, please just indicate with your hand up, and then we ask.
Yeah, let's take some questions while I.
Yeah, there's one question here from who is asking, why must we take the log before the analysis? Like I think when you talk about mutate,
Yeah.
I think like changing into when it's not normal distribution something. Yeah, he's asking why do you take the log function?
Okay, no, now it's not it's not as if you must always take the log. So the log is just one of the functions that you can use to transform your data set. But it's just that most often when you have a variable and you want to analyze, maybe you check whether it's normally distributed and it's not, you start by doing the log transformation. Log means that you're trying to constrain the value such that they can fall within an acceptable range. If you try the log transformation and it doesn't work, you can do another arithmetic transformation, maybe the square root, the cube root, the square. So log is just one of them. I just use log there as an example. It's not as if you must always use the log. And again, you transform a data only when it's not normally distributed. If your variable is normally distributed, you don't need to transform it. Okay, so always first of all check if it's normally distributed, then you proceed. But again, there are times that you might transform is still not normally distributed, then you might now need to use maybe a non-parametric test, especially when your data is small and so on and so forth. Okay.
Yeah, thanks. We have also Ekiti. Your hand was raised. Can you just unmute yourself and ask your question quickly? We don't have much time.
Okay.
Yes.
Thank you very much. I want to first of all appreciate Mr. Desmond for the fantastic job. I don't really have like a question, but I just maybe want to point out a few things on the presentation, which I think could be very helpful if addressed in details. For example, a good analysis to do a good analysis, you need to have good data. And if we're talking of good data, uh, the data must be clean. The data must follow certain norms. So, I mean, in a presentation like this, it's very important to show the audience how to import data, because most of the times, for example, when you have a project, you will not use data available in R. You will have to use your own source data. So how do you bring this data into R before you start using it is very important. My second point is, this one is maybe to add, it's important. R also has like a help function. So if you're using any function in R, you can also search within R to see the parameters of this function that you can use. So you can always use the help. If you just add a question sign before the function and you click and you run it, it will explain to you several parameters of that function that you can use. But also about the t-test, he did a t-test, which is good. I admire the fact that he explained the assumption when he got to the chi-square test that certain parameters has to be satisfied. But also for a t-test, I didn't hear the fact that, for example, you have to check for the variances. So if the variance is equal, if the variances of the two samples are equal, the test and you do the test for assuming that, sorry, if the variances for the two samples you are doing a t-test for, if the variances in those samples are different, and you do a t-test assuming the variances are equal, which is actually the default R, then you might run into issues with your results. So it's one assumption that we usually test for doing a t-test. So you check the variance first. That can be done with an f-test. So those are for me just a few comments that I had to mention. But also, when doing a regression, the regression is for normally distributed data. So you want to check that your response variable is normally distributed. If it's not normally distributed, like he mentioned, you could think of a reasonable transformation to use, like he did use a log transformation there, but also there are other transformations as he mentioned. However, if a transformation is not possible, then you should think of other statistical methods, as regression is not the only method. So you could think of non-Gaussian methods to analyze your response. So that's just what I wanted to chip in. But Mr. Desmond, great job. I follow your platform and the trainings you do. It's a wonderful exercise that you're doing. So just keep up. Thank you.
Thank you very much for the contributions. Thank you so much.
Thank you, Mr. Nkiti, and yeah.
So just like I had to mention. So we have these trainings that we offer, which last for like 8 weeks. And the trainings, we have the next session, which is starting next week on the 27th of July. We've been doing these trainings for over 4 years. So this is the 15th cohort that we are starting on the 27th of July. So I just want to use this opportunity to inform you about the trainings for those who are interested. There we go really, really detailed, looking at most of the things that the previous speaker mentioned, looking at all the assumptions. We really, really go so detailed. We needed to rush on some of these things. So registration is still open right up to the weekend of next week before we're starting on Sundays, exclusively online. We have a lot of data sets that you lay your hands on. We have weekly assignments. We have real life data sets that we do. So you can always feel free to get to us through our Facebook page, CDS Stars Academy, or you get to me personally via LinkedIn or through email, as well as the WhatsApp number on the flyer. I'll also just drop some of the links on the chat so that you can just copy them and you can get to us. And if you're interested, then we can be able to register you and we start with the training. The fees is written here is 50 euros and 30,000 francs for those who probably are in Cameroon, because I'm Cameroonian, but presently based in Belgium. So those who are abroad who want to pay through international bank is 50 euros, and it's really hands-on. And yeah, so for those who are interested, you can feel free to get to us.
Yeah, please go to the previous slide, Mr. Desmond. Don't stop. Yeah. So we are now rounding up, and I just want to quickly talk to you a bit about, to those who didn't attend the introductory part. So this is Social Epidemiology Lab. This session is brought to you. This is a monthly webinar series which we have hands-on experience on research skills, and we bring in experts like Mr. Desmond today. I'm sure many are. We also have experts among you here who are joining, who are experts in different topics related to social epidemiology. So we are an international non-profit research organization. We are based here in Germany, and we do research which tries to investigate how different social factors impact health outcome. And so we have experts in different fields: epidemiology, social science, medical science, and yeah, so we try to work together with our experience and expertise to do research that will drive impact in our community. So you can follow us. Please go back to the previous slide. Yeah, so that is our email address. Like I told you, if you need certificates for this session, please send us an email address there. We will also upload these video recordings to our YouTube channel after this session, and then I will also send out the link of this session so that via the email to everybody who registered, you can rewatch this session. And then you can also go to our website that is written there. You can follow us. You will see our team and what we are doing, our ongoing research projects all around social epidemiology, and then our publications, our collaborations. So you can, yeah, there's a lot you can learn from us. So feel free to reach out to us if you are interested in what we do on LinkedIn, on Facebook, on YouTube, and yeah, on Twitter. So thank you.
Quick question.
Yeah.
Yeah.
To Desmond, you said the trainings are weekends. Is it Saturday, Sunday?
Yeah, okay, yeah. So we're starting on Sunday. Most of our trainings are weekends, Saturdays, and Sundays.
Yeah.
And how many hours each day?
A session is 2 hours.
2 hours.
2 hours
okay.
maximum.
And,
2 hours maximum.
And it will run for 8 weeks, you said?
Yeah, minimum of 8 weeks. Yeah.
Minimum or for 8 weeks?
Yes, minimum of 8 weeks. What I mean is there are sessions that we might extend to 9 weeks based on some students might, slow to submit, and maybe we need to repeat some lessons, but to at least cover the curriculum, the detailed curriculum is at least 8 weeks.
Thank you very much.
Yeah. So you can always, even if you cannot get to us, maybe you can always get to us through the social epidemiology platform, and then they'll contact us. But we have our Facebook, LinkedIn, and my email address there. The flyer, we always post the flyer on LinkedIn, so you can follow me on LinkedIn and you always get yourself acquainted. So again, it's really, really detailed and hands-on. We really try to be patient, and we start from the very basics. And for those who are new, for those who want to advance their skills on R, for the length of time that we've been doing this for over 4 years, we'll see how we can be able to help you to get to a level where you can confidently analyze. And lastly, we also try to provide mentorship. There are people here who are students, who are researchers. They have personal data sets that they always want to analyze after the training. We don't promise to take your data and analyze for you, but of course, we always help you to mentor, provide analysis plans, and guide you on what to do, the challenges. You can always analyze, send, and we go through and help you, guide you free of charge. Again, only for people who are part of our session. So if you attend our trainings at the end, maybe you're a student, you want to analyze data for your thesis, we can always guide you on what to do in order to effectively go through your analysis successfully. All right. Thank you guys so much. Thank you. Thank you, Jude.
Yeah, thanks very much, Mr. Desmond. It was wonderful having you here. And for all those who registered and attended this session, we thank you very much. Many sessions are coming up next. Just a teaser for the July session. We'll go more a little bit away from data analysis. So in the August session, we'll talk a little bit about policy impact and knowledge transmission in social epidemiology. So yeah, so we'll go a little bit about for away from data, but we'll come back to data at another session, maybe September or so. So yeah, stay tuned to our channels, and then you'll be updated with this. And again, if you want certificates, just send us an email, and then we will take time and forward you these certificates. And then follow us, please, on our social media handles. Thank you again for everybody who could join, and yeah, wish you a great day, and then enjoy the rest of your weekend. Bye.
Thank you.
Bye.
Thank you, sir.